In this lecture, we're going to discuss a particular discrete probability distribution known as the binomial distribution. The binomial distribution is based on the concept of a Bernoulli trial, and a Bernoulli trial is simply an experiment that yields exactly two possible outcomes. So flipping a coin would be a Bernoulli trial. You have two outcomes, heads or tails. If you swipe your credit card, you have two options. The credit card transaction is either approved or it's denied. Again, that will be a Bernoulli trial. If you are in a manufacturing environment and you select an item from an assembly line, you could test that item to determine whether or not it's defective. So you have two possible outcomes, defective or not. That would be your Bernoulli trial. So you execute a Bernoulli trial multiple times, n times. We assume that each trial is independent of the other trials. So for example, if we were looking at credit card transactions and we were looking at a series of transactions that I made with my credit card, those transactions might not be considered independent because I have the same financial information, the same spending habits, the same patterns. I'm either someone who is making fraudulent transactions or I'm not. And so if we're looking at a series of my credit card transactions, those would not be independent trials. But if I'm looking at all of the credit card transactions that happen at Target on a given day, those could be considered independent because one individual's approval or denial of their credit card is really not related in any way to the next individual's. So we have these trials. The trials are independent. We execute the trial n times. We define one outcome as a success, and a success may or may not be what we would consider in sort of natural terms to be a success. A success is simply the outcome of interest. So for example, if you're flipping a coin, you might want to know the number of heads that you're going to achieve out of a certain number of coin tosses. In that situation, tossing a head would be your success. If you're looking at credit card transactions and your goal is to identify fraud, then your success might actually be a fraudulent credit card transaction. You might be interested in counting the number of fraudulent transactions that occur out of all of the transactions on a particular day at Target. If you're doing something like a medical experiment where you are testing a particular drug on 10 patients, your success might be a positive health outcome. They receive the drug and they have a positive improvement in their health. And so in that case, a success really would be what we would think of as a success. So we have our trials. The trials are independent. We execute the trial n times. We have a success that we're interested in, and we assume that the probability of success remains constant. So it's not changing over time, or it's not changing from trial to trial. So the probability that you land on heads when you toss a coin is always 50%. We assume some baseline probability or number of defectives that we would expect from a particular factory, and we assume that's not changing from trial to trial. If you have all of those things taken together, then you can define a random variable x that counts the number of successes out of n trials. And we say that x has a binomial distribution. And the parameters of that distribution are n, which is the number of trials, and p, which is the probability of a success. So for example, suppose that we toss a fair coin 3 times. We might want to know what is the probability of getting exactly one head out of 3 coin tosses. So we have our Bernoulli trial, either heads or tails. We're going to do this experiment n times, so n is equal to 3. We're going to toss the coin 3 times. The probability of a success is 0.5, 50% chance of heads if we flip the coin. We can assume that these coin flips are independent, and we want to know what is the probability that our random variable x, which is counting the number of successes, what is the probability that x is equal to 1. And so if you think about the probability on a particular sequence, the probability of getting exactly one head is just the probability of a head, which is 50%, times the probability of a tail, which in this case is actually 50%, but we're going to write it as 1 minus 0.5, times the probability of getting another tail, 1 minus 0.5. These are independent events, so we can just multiply those probabilities. And we're going to use this notation that you see here, where we're going to kind of collect like terms and we're going to write things this way, and you'll see why in just a minute. So that's the probability of getting one head. But there are multiple ways that you can get one head and two tails, right? We could list all of the possible outcomes that we could achieve if we flipped a coin 3 times. And out of those outcomes, those highlighted here in red have two tails and one head. So we can get tail, tail, head, tail, and head, tail, tail. So if we want to know the total probability of getting exactly one head out of 3 coin tosses, well, we know the probability of that particular sequence occurring, and we know how many times that can occur, so we can just do the multiplication. And if we do that, you see down here at the bottom, we've kind of collected things up, and so we have this kind of strange looking coefficient here. That's the number of ways that we can get one head and two tails. We have p raised to the number of successes, and we have 1 minus p raised to the number of failures. And we write that in this particular way because that's how we define the probability for a binomial probability distribution. The probability that a binomial random variable is equal to k, or that you achieve k successes out of n trials, is this coefficient here, which is the number of ways of choosing k successes out of n trials. So this is often read as n choose k, times the probability of a success raised to the number of successes k, times the probability of a failure, which is 1 minus p, raised to the number of failures that you would achieve. And so you can compute binomial probabilities directly in this way, as long as you know how to compute that binomial coefficient, n choose k. There are a couple of different ways of writing the binomial coefficient. Sometimes you see it with this bracketed notation, which is also read n choose k. Often you'll see it with a capital C to represent the fact that this is a combination function. And again, it's the combination of n trials, and we're going to choose k from n. The formula is using factorial notation. So if you remember in factorial notation, n factorial is just n times n minus 1 times n minus 2 and so forth, all the way down to 1. And so the combination function here is n factorial divided by k factorial times n minus k factorial. And you might say, well, that seems like a lot of work to go through just to count up the number of ways that you could get k successes out of n trials. It was relatively simple to do when we just tossed the coin 3 times, but let's suppose that you flip a coin 10 times, and now you want to ask the question, how many ways can you get 2 heads out of 10 flips? Well, if you start to write down all of the possible combinations of heads and tails that you can achieve if you have 10 coin flips, it's going to take you a while. But the binomial coefficient will really make things much more efficient. So in this particular case, if we look at 10 trials and we want to choose 2 successes out of 10 trials, we could rewrite this formula as 10 times 9 times 8 factorial divided by 2 factorial is actually just 2 times 1, which is 2, and 10 minus 2 is 8 factorial, right? And so we can just do a little simplification. So this is basically 90 divided by 2, which is 45. So there are 45 possible ways that you could get 2 heads out of 10 flips. And you can imagine with larger problems, this even just gets more cumbersome. So the binomial coefficient is just a very simple and easy way for us to count up the number of ways that we can achieve our goal with a binomial probability. For completeness, we want to define the expected value, or the long run expectation. So how many successes would we expect in the long run if we were to execute this trial over and over and over again? What would be the expected number of successes? We use the notation mu to represent the expected value, or the mean, of this random variable, and it turns out that the expected number of successes is just the total number of trials times the probability of a success, which makes sense. And we could also define the variance, and the variance again is defined purely in terms of n and p. The variance will represent as sigma squared, and that is just n times p times 1 minus p. So we can compute binomial probabilities directly from the formula, or we can use a binomial table. This particular table that you have access to is organized in a relatively simple fashion. Across the top we have the values of p, So each one of these columns represents the probability of success, and obviously this is not a complete list of all of the probabilities that you could have, but it's a fairly common list of probabilities. And then down the side we have n, which is the number of trials, and then we have lowercase x, and what this table is giving us, the values in that table are just the probability that a binomial random variable is equal to little x. Okay, and so for a particular problem we need to know the value of n, we need to know the value of p, and then we can compute our probabilities. So suppose we had a scenario where n is equal to 4. Then we're going to just restrict ourselves to this particular section of the table where n is equal to 4. Suppose that our probability of success was 0.1. And we wanted to compute a probability. We wanted to know for that particular random variable, what's the probability that x is equal to 2, for example. We would just go directly into the table. We would find our section for n is equal to 4. We would find the column for p is equal to 0.1, and we would find that intersection where x is equal to 2. And we would just grab that value out of the table. Okay, so this is kind of the old-fashioned way of computing binomial probabilities, but it is a very common way for actually doing these computations. It's the way that it's been done historically. So we're going to look at a couple of examples just to get our head around how do we actually read a problem and translate that problem into a probability statement. We'll use the table just to illustrate those concepts, and then we'll talk about how we might do this with software, which just simplifies the whole process. So here's an example. We have a student majoring in accounting. They're trying to decide how many firms to apply to when they're looking for jobs. Based on this particular student's performance, they expect that the probability of receiving a job offer from any firm they apply to is about 70%. They're feeling pretty confident, and they decide that they'll apply to 6 jobs. They'll apply to 6 firms. So in this case, the student applies to a job. They either receive an offer or they don't, so that's our Bernoulli trial. In this particular case, our success would be that the student receives an offer. Right, and our probability of a success is 70%, it's 0.7. The number of trials, n, is going to be equal to 6. We're going to see this student apply to 6 firms, and we want to ask several questions. What's the probability that the student receives exactly 1 job offer, that they get more than 2 job offers, or that they receive at most 4 job offers? And the real trick to these binomial probability problems is being able to read the question and correctly transcribe what's being asked into a probability statement, and then to correctly extract the probability from the table or using the software. So here's our first example, very similar to the one I showed you when illustrating how to use the table just a minute ago. N is equal to 6, P is equal to 0.7. And we want to know what is the probability that the student receives exactly 1 job offer. So in probability notation, this is just the probability that x is equal to 1. And we can grab that directly from the table. We'll go to the column, right, for p equals 0.7. We'll go to the section of the table for n is equal to 6, and we'll find the row of the table where x is exactly equal to 1, and we can grab that probability out, and that probability is about 1%. Now, the second question, what's the probability that the student receives more than 2 job offers? Well, we need to think about that. If more than 2, strictly greater than 2, this is kind of an elementary way of thinking about it, but sometimes people get really confused with the greater than or the greater than or equal to, and exactly which probabilities do I need to include whenever I'm actually doing this computation. So if you think about it, x is greater than 2 means that x is either 3, 4, 5, or 6. Right? So it doesn't include 2, it's strictly greater than 2. So if I wanted to compute that probability, the probability that x is greater than 2 is really the same as the probability that x is greater than or equal to 3. And so the probability that x is greater than or equal to 3 is just the probability that x is equal to 3, or is equal to 4, or is equal to 5, or is equal to 6. And so our law of addition tells us that we can simply just add up those probabilities. We can go to the table and we can grab those values and add them up, and if we do that, we see the probability is 0.93. Now, another way of thinking about this is to use the law of complements, and you'll see when we look at Excel why this is a particularly useful thing to do. Rather than computing the probability that x is greater than 2, we could think about this as the complement. So if x is greater than 2, the complement of that would be x is less than or equal to 2, right? So if x is greater than 2, the complement of being greater than 2 would be less than or equal to 2, or 0, 1, and 2. And so we could actually use the law of complements that tells us that the probability of not A is just 1 minus the probability of A. Or in other words, the probability of A is 1 minus the probability of A complement. And so that's what we've done in the second formulation here. Probability that x is greater than 2 is just 1 minus the probability that it's less than or equal to 2. If we go into our table again in the section for 6 and under the column for 0.7, we can grab those probabilities. Probability that x is equal to 0 is just 0.001 plus 0.1010 plus 0.060. 1 minus all of that gives us 0.93. So you'll arrive at the same answer either way, but there is some utility in rewriting the problem as a less than or equal to problem whenever we start using functions in Excel. And then the last question, what's the probability that the student receives at most 4 job offers? So again, if we think about this, just kind of enumerating all of our possibilities, they either receive 0, 1, 2, 3, 4, 5, or 6 job offers. At most 4 would be 4, 3, 2, 1, or 0. And don't forget about 0. Oftentimes when we think about enumerating all of the items, we don't we don't typically include 0. We typically start counting at 1. But in this case, it's entirely possible that the student gets no job offers at all, so that we have to be sure we include that probability that x is equal to 0 when we're doing these computations, so don't forget that part. To compute that probability, the probability that x is less than or equal to 4, again, we'll go into our table, we'll grab those probabilities from the appropriate section, and we'll add those up. So just be super careful when you read the problem to make sure that you understand exactly which of the integers you need to include in your probability computations. If you get that part right, the rest is easy. The table is relatively simple to use. Again, navigate the table by looking for N and P on the outer edges of the table, and then you'll narrow in on the particular row that gives you the exact value of x that you're looking for when you're computing those probabilities. So now that you have a basic idea about the probability distribution and how it works and how to convert words into probability statements, and we've illustrated that using the table, we want to move into Excel. Excel has a function called the binom.dist function that allows you to compute binomial probabilities. It has 2 different versions. If you use in Excel the argument false as the last argument in the probability computation, or in the function specification, then that's giving you an equality. If the last argument that you specify in Excel is true, then that's going to give you a less than or equal to probability, right? So if you want to know the probability that x is less than or equal to 4, in your binom.dist function, 4 would be your first argument and true would be your last argument. But if you wanted to know the probability that x is strictly less than 4, right, that's different. Strictly less than 4 is less than or equal to 3. So in that case, 3 would be the first argument in your binomial probability computation. So with that brief introduction, this will be a good time to pause and work through the interactive tutorial that will explain how to do binomial probability computations in Excel, and that will provide you with the opportunity to try this on your own. Once you've completed that exercise, you can come back to the videos and continue with the lecture on continuous probability distributions.